Well, thank you very much for giving me this opportunity. You've heard from John Kelly about the future. Now, making predictions is very difficult, especially about the future. But my job here is to tell you something about how we got here over the last 30 years and lessons we learned. So I want to take you back to 1987. I had been invited by John Dertouzis to give a distinguished lecture in the computer science laboratory at MIT. Very prestigious. Now, they had a tradition was that the speaker would meet with the faculty for lunch. Now, this was an area of good old-fashioned AI, symbol processing, rule-based, expert systems. As we're going up the elevator, Dertouzis tells me, by the way, you know, they hate what you do. And you're going to get 5 minutes before they start asking you questions. And literally, I walked into this big room. The whole computer science AI lab was there. Senior faculty in the first ring, you know, then the junior faculty, and then the students. And I just, you know, had literally 2-minute warning. So here's what I said. I want you to answer this question, okay? Here we have a honeybee. This honeybee has 1 million neurons. You have 100 billion. But it can see, it can fly, it can mate and reproduce itself. Now downstairs you have a supercomputer, Cray area supercomputer, $100 million computer. It can't see, it can't fly, and the NSA has tried to get them to mate, but it has failed every time. What is wrong with this picture? And dead silence. Dead silence. And I knew at that point the Lord had delivered them into my hand. So one of the senior faculty put his hand and said, well, we haven't written the vision program yet. And I said, why not? And then Gerald Sussman, who's a very smart guy, said, well, we know from Turing that anything that is computable can be written down as a program. And I said, well, how long will that take? So it turns out that they didn't have a clue. But there was one student in the background who put up his hand and said, well, the difference is that the digital computer downstairs is a general purpose computer. It can compute anything very, very inefficiently, whereas the brain of this little creature here is a special purpose computer. And that was the right answer. And standing in the background was Rodney Brooks, who was, you know, relegated to the third tier, who later became the head of the AI lab. He was a roboticist who actually decided that he would build biologically inspired robots. Now, if you go back to the origins of digital computing, it all is based on Boolean logic. This was a book that George Boole wrote in 1854, and let's just look at the title here, An Investigation of the Laws of Thought on which are founded the mathematical theories of logic and probabilities. So we know we've been focusing here on logic for the last 50 years, but probabilities is what has actually gotten us as you know, survive in the real world based on probabilities. That's really what you need to compute in order to keep track of things that are happening that are uncertain. And really, it's been the last 30 years, it's been how to automate probabilities. Now, before the digital computer, it was humans who were hired to compute. And I remember going through school computing with 2 blocks of wood. How many people out here use a slide rule? Okay. So, I mean, this was state of the art, you know, 50 years ago or so. This is Pat Churchland, who's a co-author on the computational brain. This is a picket. And as you can tell, even back then, they were trying to scale it up. But, you know, it turns out that there are many ways to compute. For example, suppose you want to sort numbers. Here's a bunch of numbers. Okay, you know, we can write a program. There's a lot of sorting algorithms. But here's a way to do it using spaghetti. You do it. You get a lot of strands, and then you cut each piece to the length of that number, and then you just go whack and pick out the highest one and the second highest one and so forth, right? So what's going on here is you put a lot of effort into building the machine, and then with one trial, with one operation, you solve the problem. Now, you might say sorting, this is a useless problem and from the point of view of having to put all the effort into building the spaghetti. But let's take a problem which is to find the shortest distance between two cities. Okay, again, you can do it by just brute force search. Here's a string computer that can do it. What we do is we put, get us some string and connect up the length of the string proportional to the time to drive between the cities. And then, if you've put an effort into creating this big crochet device, and now if you want to know the distance between Seattle and Miami, you pick them up by those two knots and stretch it. And the shortest distance is across the top. Now, the beauty of this computer is that you can now use this over and over again for any pair of cities. You pick it up and stretch it. And I think this is a metaphor for what happens in nature, is that a tremendous amount of effort is put into developing your brain. And in humans in particular, our educational system, that's really the equivalent of creating the strings, of trying to program through experience and create a system such that you can come up with answers to very difficult questions in one trial. This is what John was telling us about, the experts in Jeopardy and an expert doctor. The really good ones can tell you immediately what the problem is. Okay, well, what kind of a computer is the brain? Well, first of all, it's not a digital computer. Well, what kind of a computer is it? Well, one of the problems with that question is that it's not a single computer. There are literally hundreds of different computational problems that are solved by specialized circuits, special purpose circuits, and one of the things about a special purpose circuit is that it's hardwired to do the job really efficiently, really well. And what's going on right now is deconstructing those circuits to find out what the algorithms are that actually is being implemented there. In many cases, we don't have a clue. But some basic facts. We have a large number of neurons. The key thing is each one is connected up to about 10,000 other neurons, high degree of connectivity. These are not simple devices. Each one of these neurons itself has enormous computational capability on many different timescales. And what we've been trying to do is ask the question of what can you compute if you have a lot of little simple devices like this? And one of the answers very early on, from going back to the perceptron era, Frank Rosenblatt, is that you can learn by example. You give a lot of positive examples, a lot of negative examples, and if it's linearly separable, this algorithm will produce a classifier that will allow you to take new items that you haven't seen before and correctly classify them. Now, this is back in the 50s. A very influential book was published by Minsky and Papert, mathematicians who analyzed it and showed that this could you could only learn linearly separable functions, and they stated that we do not think it is possible to generalize this to a multi-layer network. Now, this really stopped research because everybody believed it. Minsky is a very smart guy, and Minsky couldn't imagine a solution to the problem. He must be right. Never trust an expert if they say something is impossible. Well, it was in 1983 that Jeff Hinton and I developed the first analytical solution to a multi-layer network. We call it the Boltzmann machine. It was probabilistic, very simple learning algorithm, and we know a lot about this now. Yoshua Bengio has been one of the leaders in extracting, analyzing, and using Boltzmann machines, and so has Jeff. But this opened the dam. It just flooded because we now have many learning algorithms. In fact, we know that the brain has at least a dozen different learning systems working together, very interpenetrating. And one of the first applications that kind of gave us an idea that this might be a better way to do human tasks, difficult tasks like vision and speech, was something called NetTalk. And this is a student of mine, summer project. What we did was we took inputs were text, just letters, and the output were the phonemes associated with each letter. English is a particularly difficult language to learn because it's so irregular. And literally within a day of training, we were able to teach the network to pronounce a 20,000 word dictionary correctly. So, and this is a tiny, tiny network with just 80 hidden units. It really was at the time, with the computing power was available, was megahertz machines. It was VAX 1 era. But it was a demonstration that at least some problems might be solvable. Fast forward, 30 years later, we now have networks that are 20 layers deep. And this is, in fact, the architecture of your brain. If you look into the cortex, each one of these little boxes is a cortical area. There are hundreds of cortical areas. This is just the visual system, right? Several dozen visual areas, about a dozen layers deep. Now, what is the secret of any computing system if you want to have practical applications? The secret is it's got to scale, and most algorithms don't. NP-complete is the worst. Exponential scaling. Even polynomial scaling will kill you eventually. So the real secret of these learning algorithms that we developed in the 80s, the secret is that they scale beautifully. The larger the network, the more data you have. And now, 30 years later, computers are a million times faster. Internet data is available freely. And now we've discovered is that it actually can solve practical problems. Now, it's not the only way to solve practical problems, but whatever the solution is, it's got to scale. Otherwise, you're dead in the water if you want it to make it any bigger. Now, you've already heard about deep learning. I'm not going to tell you much about this except to say that this is ConNet from Jan LeCun. It turns out that almost every part of this network is based on a biological architectural feature of our visual system. Convolution on the first layer, those are linear filters, simple cells in the visual cortex. Pooling, this is what the complex cells do in the visual cortex. And then there's normalization. Each one of those parts of the network really have this analog in the biological system. And we have much to learn by actually following that up and seeing what happens at the various highest level, where invariances are pulled out, where you can recognize objects, where you can detect anomalies, for example. However, there's one fact about your cortex and your brain that isn't captured by these feed-forward networks. It's the fact that for every feed-forward connection, there's a feedback connection. Information goes up, information comes down. Information also circulates. And in order to get a system that has recurrent connections, you need to tame the nonlinearity. Positive feedback loops are very, very difficult because they tend to blow up. And it was John Hopfield who tamed them back in 1982. He showed that with the right architecture, you could use a recurrent network to store information in a very elegant way. And in fact, that was the origin of the Boltzmann machine. Basically, we heated up the Hopfield network probabilistically. So let's marry the feed-forward architecture with the recurrent network. And this is now from the last NIPS meeting in Montreal in 2014. We can recognize objects and scenes with a deep neural network. We couple that with a recurrent neural network and train it up to describe what's going on in the scene. For example, in this particular scene, you can see it's a kind of a marketplace, and here are this is a test image that wasn't given as part of the training set, a group of people shopping at an outdoor market. That's a pretty good summary. There are many vegetables on the fruit stand. Well, I'm not sure how, does it look like bananas? It's possible. But it's really, what's amazing though is how well it does on a whole set of different images. Again, a woman is throwing a frisbee. Not only does it tell you what is in the scene, but it actually can point out for each word where it got the information. A dog is standing on a hardware floor, a stop sign, a little girl, a group of people sitting in a boat, a giraffe standing in a forest. The trees are part of the background. This, I think, is something we could have never predicted. I would have never even imagined this would be possible, but this is now becoming state-of-the-art, and people are now really beginning to appreciate that a lot of things that we thought were very, very difficult, natural language processing, is within the capability of these networks. Now, Watson has even more sophisticated natural language processing, but marrying these two technologies is a marriage made in heaven, or ad nips. The next meeting will be again in Montreal. It's unbelievable how many, last year we had 2,500 researchers. Every major internet company, Google, Microsoft, were there recruiting. It's very difficult now actually to get students in computer science departments to work on machine learning because they're all getting very big salaries in Silicon Valley. I want to come back now to the bee. The bee is a champion learner. Now, the talk that I was giving at MIT was on research that was done by a postdoc, Jerry Tesaro, who's now part of the Watson team. And he had taught a neural network to play a decent game of backgammon. So after leaving my lab, he went to IBM, where he perfected it. And he used an algorithm that is probably the most primitive learning algorithm in your brain. It's called classical conditioning. And it had been shown that in the bee, there is one neuron that gets conditioned through experience. For example, if you give a bee a reward, like in this case, it's sucrose solution, nectar, and associate that with a color of the flower or the odor of the flower, it will then go back to flowers with the same shape, odor, and size, and it can even tell other bees using a waggle dance. Very smart little creature, million neurons. Well, it turns out that the algorithm that is being used there, the classical conditioning, can be understood as a reinforcement learning system using temporal difference learning, where you learn to associate with weights, the sensory input with the reward, and you use the difference in your prediction between the reward you predicted and the reward you got to update the weights and make decisions. TD learning. So it turns out that we have neurons in our brain that help us make decisions. They're called dopamine neurons. And Wolfram Schultz, a neurophysiologist, recording from those neurons in monkeys, showed that they have exactly the properties of this algorithm. By the way, Wolfram Schultz is the one here on the right. And this is a fantastic story having to do with addiction and word learning, but I don't have time for that, except to say that Jerry, taking a page from the book that Samuel at IBM had written earlier, got this computer program to play itself, and used temporal difference learning and a backpropagation network to train it up. And it got to the point where it was actually doing better than Jerry. And at that point, he got Bob Roberti to come, and he was amazed because he said, this program's playing better than any game program that I've ever seen. He took notes. By the time it got up to 1.5 million, it played him to a standstill. And it was making decisions, very complex decisions, about whether to build up a defense or whether to run for the goal that even humans find difficult. It was really phenomenal. And he said at this point, it probably could have won the international championship in backgammon. Now, how many people here know about TD gammon? You're all IBMers, okay? But you probably have heard about it. But you probably have, most of you have, everybody here has heard about Kasparov and how the Deep Blue program beat Kasparov, and it was 1996 or 1997. Well, I think this achievement is much more important than that, the chess playing machine. That was brute force. This is real learning and creativity, in the sense that it was coming up with moves, positional moves that no human had ever made before, which subsequently were shown to be better than the crowd's, the wisdom of the crowd. So I think this is really a very, very important piece of research, and in fact has served as kind of a flagship for the reinforcement learning community over the last 30 years. Now finally, and here's the point I want to make, which is that classical conditioning is a very weak algorithm, but when you couple it with a very powerful cognitive computing capability, it's amazing what it's capable of doing. And this is another example of an expert who was dead wrong. Noam Chomsky wrote a very influential essay back in the 60s, in which he said he could not imagine classical conditioning being able to learn language. And since Noam Chomsky was the smartest linguist in the world, people believed him. Argument from ignorance. Just because you can't imagine it doesn't mean it's not possible. And I've already given you an example of language learning that is actually a counterexample to Dr. Chomsky. Now here's another counterexample. This is a group, a DeepMind group in London, now part of Google. And what they did is they used reinforcement learning, TD, and coupled it with deep learning to play games. This is Atari games that go back to the 60s. And here's the level of human performance. And you can see all these games it's playing, and it has learned simply by getting input from the screen, pixel by pixel input, and reinforcement at the end of the game. That's the only input it gets. And it achieves almost, in fact, superhuman performance in many of these games. Again, multiple learning algorithms coupled together, and that's, in fact, the architecture of the brain. Now, finally, we can actually build the hardware. And Carver Mead at Caltech was one of the early pioneers, pointing out that if you build the algorithm into the chip in the same way that nature builds the algorithms directly into the circuit, that you could have much more efficient computing. Cheaper, less power, more efficient. I want to give you an example of, this is Toby Delbrook, who was a student of Carver Mead, who built this little camera. It's a very simple camera. Each pixel has two different outputs. One output gives you a spike every time the voltage goes up by an increment, and the other output gives you a spike every time it goes down. So you're basically encoding changing gray levels in the form of a bunch of spikes. And by the way, this is how your retina works too. On-center and off-center ganglion cells. Everything you see in here are converted very quickly into spikes. Everything you see right now is just a pattern of spikes in your brain. There is no frame buffer. And an ordinary camera that you have has frames that are like 30 milliseconds, where it accumulates gray level and then stores it into a memory. But the question is, what can you compute with spikes? So here's the camera, and you're going to see it now, in fact, as we pointed at Toby. First of all, you get no output unless there's something moving. So the background is gray, that's no spikes. Positive are white, negative is black. And you can see that it highlights the things that are important. Very efficient in terms of information compression. And you can put it through a sunglass and you can see the same information because it's just changing the overall gain. There's a Scientific American article if you're interested. Now here is, I think, the key. So this is a rotating dot, and you can see that if you have a large time slice, 30 milliseconds, you see nothing. All you see is a circle. But as you slow it down to 100 milliseconds, you can very easily figure out what is moving and compute the velocity with just a few spikes. Computer vision has been bedeviled by the fact that if they start with frames, and if you've thrown away the information, you can't recover it. It's now looking, this is Zurich, you're hearing a single pixel as you go through the town. That's what your brain is listening to. Well, here's that helix. The point that I'm trying to make here is that it's really important how you encode the information at the very earliest stage, and that makes the algorithms upstream much easier. Now, we can actually start. This is a sensor. We have put a lot of effort into it. But what about the computing that has to be done downstream. How are we going to do that? Well, I'm leaving that up to Dharmendra, who has built this True North chip, which in principle, with simulating 1 million neurons and then scaling it up, could, in principle, create a visual system that works as well as ours. Could, with reinforcement learning, make decisions, perhaps as good or bad as ours. We're not trying to duplicate the brain, but we're trying to use architectural features of the brain to try to understand how to put together these complex systems. Finally, 2 years ago, a grand challenge was announced by the White House, which is called the Brain Initiative. How many people here have heard about it? Maybe I should have said who haven't. So the key words here are innovative neurotechnologies. The goal here is to try to bring engineers into neuroscience labs to help us to record more neurons, to analyze the responses, the properties of the neurons, and ultimately to get a much deeper understanding of the general principles that then we could take away and build cognitive computers that are even more powerful than we have now. Now, this was not the first country. We were not the first country to make an announcement. In fact, the European Union came out with their own human brain project a year before the US. Theirs was €1 billion. Ours is 5 billion American dollars. I was on the committee that actually made the recommendations to NIH, so I know a little bit about what went into that. China has not yet announced their program, but I have friends in China, and I know a little bit about what is happening there. They had earlier developed a plan to try to focus on human brain diseases like schizophrenia, Alzheimer's, and so forth, which of course we all want to cure, right? Very difficult problems, out of the reach of current technology, but maybe with better neurotechnology we'll make some progress. So that was going to be their announcement until the military got involved. Now the military, I think, in China may be as smart as Watson here at IBM, because they smelled a technology that would be coming out of that, which would be very important for the future of China. And they were willing to put in a lot more money. They haven't announced it yet, but the numbers that I'm hearing, $1 trillion. That turns out to be about the size of the investment that the United States made in the Apollo project, about $100 billion. And that had a tremendous transformative impact on technology in the United States. Microelectronics grew out of that era, materials, space industry. Every one of these grand challenges, it was an investment in infrastructure, both material and intellectual, which really had a huge impact on the country. The same thing is true of the other ones, the Human Genome Project. It's now a multi-billion-dollar company. For every dollar invested, we now have $140 worth of increased economy. And you can't get a return that high by betting on the stock market. So let me now finish by just taking a very broad view and really looking back in history and trying to understand maybe what we're going through, this transition that John was telling you about. If you look back at physics in the early 20th century, these were the great discoveries were made in quantum mechanics and relativity. But it wasn't until the second half of the 20th century that they became products like laser pointers, right? It takes that long to go from proof of principle to a technology to something that is used by the masses. Now, what fundamental discoveries were made in the second half of the 20th century that are just now seeing technological significance? DNA was the structure of DNA was determined by Watson and Crick in 1953. That completely transformed biology. The tools and techniques that are now available, recombinant DNA, CRISPR technology for changing your own genome, that all was done worked out in the second half of the 20th century, and now personalized medicine, precision medicine, is really going to transform healthcare, and it's going to transform a lot of other things too. But the point is that it takes that long to go from proof of principle, scientific advance, to something that affects everybody walking around. So what's going on here in the 21st century? And this is now, I'm going on a limb here, trying to make a prediction, so sorry if I disagree with anyone. Well, what's clear to me is that everything we do now depends on computers. And that's true, by the way, of neuroscience. We could not have collected the data or analyzed it without the fact that there's cheap computing. Computer science really is powering everything that is happening today. But we also have created a nanoscience, which is allowing us to build ever smaller devices that, again, is very important for transforming how information, for example, is stored and how it's accessed and how it's used. And finally, nature was there long before us, because that really is the secret of the brain. The secret of the brain is, how do you handle huge amounts of information? Every day you walk around, it's like a fire hose that is coming into your brain through your sensory systems. You have to figure out what to do with it, how to store it, how to integrate it. All of these mysteries are going to be worked out over the next several decades, over at least the first half of the 21st century. We're going to know answers very, very soon. And what do these all have in common? Information. It's all about information in all of its forms. DNA is information. The brain is the organ par excellence for handling information. And how do you organize it? How do you access it? How do you apply it? These are the big challenges that we have now over the next several decades. And I'm really very, very pleased that IBM is taking the leadership role, because it's so important that we have partnerships with industry. Now, we've heard big data is really the key to it all. Without the human in the loop, the big data is not going to be, it's not going to give us the answers. Absolutely right, it's a partnership between the human and the data through these platforms. And if I could make, I think, a very safe prediction about the future is going to be even bigger data. So I want to thank everyone and all of my mentors and collaborators. Thank you.